After studying this module, you shall be able to know the interaction of internal electric field due to vibrations in molecule and the external field. You will also learn the selection rule for infrared spectroscopy. You will also learn about IR vibrational active modes of water molecules, IR active modes, vibrational modes for POCl3 molecules. You will also learn the selection rules for Raman spectroscopy. You will learn about Raman vibrational active modes for water molecules and vibrational active modes for POCl3 molecule. You already know about reducible and irreducible representation and how to get these representation by taking 3n vectors as basis. You have also learned how to get irreducible representation corresponding to x, y, z, rx, ry, rz vectors. That is how to find tau t, tau r. Tau vibration were then obtained by subtracting tau t, tau r from tau 3n. In this module, we will learn about selection rules and infrared spectroscopy and Raman spectroscopy. In spectroscopy, selection rule or transition rule formally constrains the possible transition of a system from ground state to excited state. Here, selection rules have been derived for vibrational spectroscopy. The selection rules may differ according to the techniques used to observe the transitions. A vibrating bond in a molecule behaves like oscillating electric field, and there is a change electric dipole moment. Electromagnetic waves in the region of infrared also have electric field component with it. When internal electric field component due to vibrating molecule interacts with the external electric field component of the electromagnetic waves, the transitions from ground vibrational state to higher vibrational excited state may occur or not. That is, this transition is allowed or not. In this section, we will learn the selection rules about these type of transitions. According to quantum mechanical rule, delta nu is equal to plus minus 1, that is the transition from nu 0 to nu plus 1 is allowed. In quantum mechanics, this basis for infrared spectroscopy selection rule is the value of the transition moment integral of the type as given in equation 1, that is integration psi g star mu psi e dot t. Transition occurs from vibrational ground state, that is the initial state, psi g, to vibrationally excited state, psi e, by absorbing one quanta of energy. This is called fundamental transition. The mu is molecular dipole moment vector. The probability of such transition from psi g ground vibrational state to psi e first excited vibrational state is directly proportional to transition moment given by the integral of the type as given in equation 1. Since psi g ground state wave function is always real, we write down psi g star as psi g, and the equation 1 can be rewritten as integration psi g mu psi e d dot t. Dot a means integration is carried out from all variables of the wave function. The spectroscopic activity of a vibrational modes depends upon the value of transition moment integral, that is psi g mu psi e. If this integral has zero value for a particular transition, then the probability of occurring this transition will be 0 and no absorption of IR radiation will occur. Thus, the transition is forbidden, vibrational will be vibrationally inactive. If the integral is non-zero, then there will be absorption of IR radiation by the molecule and the transition will be allowed. Hence, it will be IR active. In practice, the integral itself does not need to be calculated to determine a selection rule. It is sufficient to determine the symmetry of transition moment function, that is psi g mu psi e dot t. The idea of symmetry is important when considering the integral of the odd functions, since psi g ground state wave function is always real and symmetric. It follows that for a vibration transition to be allowed, the symmetry of the excited state wave function must be the same as the symmetry of the transition moment operator mu. Solving of integrals of the type psi g mu psi e dot e is cumbersome process. Group theory helps and simplifies the solution of such integrals. According to group theory and symmetry consideration, if the direct product in this integral contains totally symmetric representation, that is an irreducible representation for which chi is equal to +1 for all symmetry operation of the point group, then the integral will be non-zero and there will be interaction between electric field component of electromagnetic radiation, that is in the IR region, and the electric field component of the oscillating electric dipole moment of the vibrating molecule. Hence, absorption of IR radiation will occur and vibration will be IR active. Thus, only difficulty left in assigning the spectroscopic activity to the vibrational mode is to solve the integral, the transition moment integral psi g mu psi e dot. It can be resolved. This equation can be resolved into three components along x, y, z axis, and these resolved integrals can be written as given in equation 2, equation 3 and equation 4. Equation 2 says psi g mu x psi e dot t. Then equation 3 says psi g mu y psi e dt. Then third one, that equation 4 psi g mu z psi e dot t. If any of these integrals given by equation 2, 3, 4 is non-zero, then according to symmetry point of view, this transition will be allowed. So, problem now is to find how to check the symmetries of the direct product in this three component integral. We know that the vibrational ground state mu 0 is 0, that is psi g has mathematical symmetry to that of s orbital. Since a sphere is totally symmetrical in a point group, the ground vibrational state psi g will be totally symmetrical for all molecules. Symmetries of the component of transition moment vector mu x, mu y, mu z is the same as that of x, y, z axis or that of translation vector tau x, ty, tz. Their symmetries can be directly obtained from the character table of the point group to which the molecule belongs. The symmetry properties of vibrationally excited state psi e are then the same as that of the vector which describes or forms the basis for the particular vibrational mode, that is tau vibration. So, we have to evaluate the direct product of psi g, that is a totally symmetric, the irreducible representation for which x, y, z axis or tx, ty or tz form the basis for representation of that, and psi e irreducible representation of the vibrational modes to be considered for the IR activity, that is spectroscopic activity of which we want to determine. In the integral psi g mu psi e dt, the direct product of psi g psi e will give the product as psi e. The direct product of a totally symmetric irreducible representation with non-symmetrical irreducible representation equals to non-symmetrical irreducible representation. For example, in C2V point group, A1 B1 is B1. So, direct product mu into psi e must contain totally symmetrical irreducible representation in it. So, we have to check now the symmetry of mu, that is mu x, mu y, mu z. The symmetry of psi is the same as that of the irreducible representation, the activity of which we want to know, and it is given a normal mode belonging to any symmetry species as that of x, y, z axis or tx, ty, tz translation vector will be IR active. Symmetric characteristics of transition moment operator is summarized in the table as such. That is, type of transition we will consider electric dipole and mu transforms as x, y or z, and it is used in infrared spectroscopy. Electric polarizability and mu transforms as x square, y square, z square, xy, xz, yz, etc., and it is used for Raman spectroscopy. Now, to explain the point made so far in this module about vibrational transitions, let us take the example of water molecule or SO2 molecule which belong to C2V point group. In earlier model, we have obtained tau 3n and then tau vibration as 2A1 plus B2 for water molecules. Now, we will find the activity of A1 mode and B2 modes, that is that of psi e, which belongs to either A1 or B2. Symmetries. In C2V point group, the totally symmetric representation is A1. We have to find out the irreducible representations for which x, y, z axis or tx, ty or tz form the basis for representation. That is, we have to look for symmetry spaces of mu x, mu y, mu z as etc. using character table of C2V point group as given. The symmetry of these vectors are listed as. Now, let us see the symmetry of mu x, that is equal to Tx or x belongs to B1, symmetry. We have to see that is X belongs to B1 symmetry. Now we go for mu y and we look Ty or y belongs to B2 symmetry. We see the column for X and Y and then we see the column for irreducible representation. Then we see Tz or Z belongs to A1 symmetry. That is, in this case, mu X belongs to B1 symmetry, mu Y belongs to B2 symmetry and mu Z belongs to A1 symmetry. Now check the activity of two A1 mode and B2 modes. We have to evaluate direct products. Check whether the direct product equals to or contain totally symmetric irreducible representation in it. Let us take first psi g mu x psi e dt, that is integral A1 direct product B1 direct product A1 and it is B1, that is net direct product is equation 5, that is B1. Let us take the second integral psi z mu y psi e dt and the corresponding direct product equation is A1 direct product B2 direct product A1, it is B2, that is equation 6. Let us take third component psi g mu z psi e dt and the direct product is given by A1 direct product A1 direct product A1 is equal to A1, equation 7. Here psi z has A1 symmetry, mu x, mu y, mu z have B1, B2, A1 symmetries respectively. Psi e has the same symmetry as that of A1, B2. Out of three integrals given by equation 5, 6, 7, if any of these contains totally symmetric representation, that the vibrational mode will be IR active. Out of these three equations 5, 6, 7, the direct product integral given by equation 7 contains a totally symmetric representation A1. Thus, the overall integral psi z mu psi e dt has A1 representation in it and thus the integral is non-zero. Hence, the vibrational mode is IR active, or we can say A1 mode is IR active. Let us check the activity of B2 mode. For this, we have to consider direct products and let us evaluate them. The first direct product, that is psi z mu x psi e dt, and the direct product is given by equation 8. A1 direct product B1 direct product B2 and the result is A2, equation 8. Similarly, let us take other integrals psi e mu y psi e, that is dot deta is equal to A1 into B2, it is A1, equation 9. Third integral is psi z mu z psi e dt is equal to A1 into B2 is B2. Out of these equations, that is after solving integral 8, 9 and 10, equation 9 contains totally symmetric representation. Hence, overall integral contains A1 mode and thus it is non-zero, and B2 mode is also IR active. Thus, in tau vibration for water molecules or SO2 molecule, 2A1 plus B2 mode, both modes are, that is A1 and B2 modes are IR active in this water and SO2 example. Now, we can take another example of C3 viewpoint group, that is we can take POCl3 or chloroform CH-Cl3 molecules. We obtained tau3 as in earlier model, and we have shown that tau vibration comes out to be 3A1 plus 3E for POCl3 molecule. Now our job is now to find out the activity of A1 and E modes, that is psi E belongs to either A1 or E symmetry. In C3V point group, the totally symmetric representation is A1. We have to find the irreducible representation for which x, y, z axis or Tx, Ty, Tz form the basis for representation, that is symmetry species of mu x, mu y, mu z component. Using again the character table of C3V point given as given over here, symmetries of these vectors, that is of x, y, z or Tx, Ty, z vectors are then obtained, and these symmetries are listed as mu x represents Tx, or you can say x belongs to E, or mu x has the symmetry as that of E irreducible representation. Similarly, mu y is equal to Ty, or y belongs to E symmetry. That is, here mu x and mu y both belong to E symmetry. Mu z, that is Tz or z, belongs to A1 symmetry. In order to find the activity of A1 and E modes, we have to now evaluate the following direct product integral. That is, we have to check the activity when psi E has the symmetry as 3A1 and 3E, whether these are IR active or not. For this, we have to consider the integrals of the type given. For A1 mode, we have to solve the integrals given by equation 11, 12 and 13, that is psi z mu x psi E dt, that is A1 into E into A1 is E. Equation 12 psi z mu y psi E dt, that is A1 into E into A1 is E. Then we have psi z mu z psi E dt, A1 into A1 into A1 is equal to A1, equation 13. Out of these equations, that is 11, 12 and 30, the equation 13 or the direct product given by equation 13 contains totally symmetric representation. Overall integral is non-zero. Hence, A1 mode is IR active. Now, let us take E mode and check its activity. For this, we have to consider direct products and evaluate these direct products as given in equation 14, 15, 16. That is, we consider now the direct product psi z mu x psi E dt, that is A1 into E, that is A1. Then psi z mu y psi E dt, that is A1 into E is A1. Then the third one psi z mu z psi E dt, and that is A1 into E, that is E. Out of the integrals given by or the direct products given by equation 14, 15 and 16, equation 14 and 15 contain the totally symmetric representation A1. So, overall integral is non-zero. So, the vibrational mode EE is also IR active. Thus, in tau vibration, we find 3A1 plus 3E modes, that is both A1 E modes IR active for POCl3 or chloroform, that is the molecules which belong to C3V point group. Let us now go to the another topic, symmetry selection rules for Raman spectroscopy. In Raman spectroscopy, transition between vibrational states can be described in similar manner as we have done in the case of IR spectroscopy by the integral of the type psi z alpha psi e dt as shown in equation 17. Here psi g and psi e represent the ground and the first excited vibrational excited state. Alpha describes the polarizability of the molecule under investigation. Raman effect depends upon the extent of induced dipole by the laser beam. Induced dipole moment is directly proportional to polarizability of the molecule, that is P is equal to alpha E. Polarizability means the extent to which electron distribution in the molecule can be distorted by the applied laser beam. As mentioned earlier, alpha is a tensor with 3 into 3 array of component. Terms such as alpha xx, alpha xy, alpha xz, alpha yz, alpha zy, alpha like this we are having alpha z, which are given by over here in matrix form px, py, pz is equal to then all component terms alpha xx, alpha xy, alpha xz, alpha yz, alpha yy, alpha like this, and we are having ex, ey, ez, that is the equation p is equal to alpha e can be represented in matrix form over here. For vibrational transition in Raman spectrum, alpha jk is equal to alpha kj, where jk are nothing but x, y or z. Therefore, out of 9 terms in matrix, only 6 terms are to be considered. Alpha xy is equal to alpha yx, alpha zx is equal to alpha xz, alpha yz is equal to alpha zy, alpha xx or alpha x square, alpha yy or alpha y square, alpha zz or alpha z square. Thus, there are 6 distinct components of the integral psi z alpha psi e dt, and these integrals are given as in over here numbering 1, 2, 3, 4, 5, 6. That is the first integral is psi z alpha xx or x square, psi e is dt. Second integral is psi z alpha yy or y square, psi e dt. Third is psi z alpha zz, that is z square, psi e dt. Fourth integral is psi g alpha xy or yz, psi e dt. Fifth integral is psi g alpha yz equal to zy or psi e is dt, and sixth is psi z alpha zx xz psi e. That is, we are having 6 integral in this equation. For a vibration to be Raman active, any of the above 6 integral should be non-zero. We need to find the symmetry of direct product of these integral. Psi g is totally symmetrical, and symmetry of alpha xy is equal to alpha yz, alpha yz is equal to alpha zy, and alpha zx is equal to alpha xz. Then alpha xx, that is alpha x square, alpha yy, that is alpha y square, alpha zz, that is alpha, is the same as the symmetry of the binary functions, that is xy is equal to yx, yz is equal to zx, zx is equal to xz, x square, y square, z square. And for this we have to see now the last column of the character table. Symmetry of these binary functions can be noted down from the last column of the character table of the point group. After saying something about the polarizability, let us again the both example for C2b point group and C3b point group, and let us try to check up the activity of the vibrational modes for this molecule. Now, in earlier model we have obtained tau 3n and tau vibration for water molecules or SO2 molecules which belong to C2b point group, and the result is given as tau vibration is equal to 2A1 plus B2. Now, we have to check the Raman activity of A1 and B2 modes, that of psi E, which belongs to either A1 or B2 symmetry. In C2b point group, the totally symmetric representation A1 is A1. For Raman activity, we have to find the irreducible representation for which the binary functions xy, yz, zx, x square, y square, z square form the basis for the irreducible representation. That is the symmetry spaces of xy, xz, then alpha x square, alpha y square, alpha z square, or we can say alpha yz, etc. That is, we have to look for the symmetries of this 6 component. Now, let us see the character table of C2b point group, which is given over here. And again, now let us check the symmetries spaces for this. Symmetries of alpha xy is A2, symmetry of alpha yz is B2, symmetry of alpha xz is B1, and symmetry of alpha x square is A1, symmetry of alpha y square is A1, symmetry of alpha z A square is A1. For checking the Raman activity of A1 mode, above 6 direct product integrals can be written as: number 1, A1 into A1 into A1 is A1. Number 2, A1 into A1 into A1 is A1. Number 3, A1 into A1 into A1 is A1. Number 4, A1 into A2 into A1 is A2. Number 5, A1 into B2 into A1 is B2. Number 6, A1 into B1 into A1 is B1. Integrals out of this 1, 2, 3 all contain A1 representation. Thus, the whole integral mu psi g alpha psi e dt is non-zero, or A1 mode is Raman active. Symmetric modes are Raman active and always polarized. For checking the Raman activity of B2 mode, above 6 direct product integrals can be again written down in 7, 8, 9, 10, 11, 12. That is, 7 number says A1 into A1 into B2 is B2. 8th says A1 into A1 into B2 is B2. A1 into A1 into B2 is B2. And the 10th integral says A1 into A2 into B2 is B1. A1 into B2 into B2 is A1. A1 into B1 into B2 is A2. Of these 6 integrals, integral 11 or the direct product 11 contains totally symmetric representation. So, the whole integral is non-zero. Hence, B2 mode is also Raman active. So, in water molecules, both vibrational modes 2A1 plus B2 Raman active, or we can say that both these modes are IR active as well as Raman active. Now, let us take another example, that is POCl3 or chloroform. These molecules, they belong to C3V point group. For C3V point group, as we have obtained earlier, tau vibration is given as 3A1 plus 3E. So, we have to now check the Raman activity of these modes. Using the character table of C3V point group, symmetry component or symmetries of alpha components are noted as alpha xy is E, alpha yz is E, alpha zx is E, alpha x square is A1, alpha y square is A1, alpha z square is A1. And psi E is either of A1 symmetry or E symmetry, that is, we have to check the Raman activity of A1 and E modes. Now, let us, for this we have to consider now 6 direct product integral of the integral psi z alpha psi E dt for checking the activity of A1 mode. These can be written down in equation 13, 14, 15, 16, 17 and 18. And these direct products are A1 into A1 into A1 is nothing but A1, A1 into A1 into A1 is equal to A1, A1 into A1 into A1 is A1. And similarly, we have for integral 16, 17 and 18 as A1 into E into A1 is E, A1 into E into A1 is E, and the last one A1 into E into A1 is E. These integrals 13, 14 and 15 contain totally symmetric representation, that is A1. So, the whole integral is non-zero. Hence, A1 mode is Raman active. So, for POCl3 CH-Cl3 molecule, all vibrational modes 3A1 plus 3 are Raman active, and we have already seen that these are also IR active. So, in both these molecules we have considered so far C2V and C3 point group molecules, we have noticed that all the modes are both IR and Raman active. Now, for centrosymmetric molecules, that is molecules which have center of inversion, the mutual exclusion principle applies. According to this rule, there exists no common vibrational modes which is active in both IR and Raman simultaneously. A vibration which is active in IR will be Raman inactive and vice versa. The reason for this is that Tx, Ty, Tz, which form the basis for vibrational modes, are antisymmetric with respect to I. That is, these are unzeroed, whereas the product x square, y square, z square, etc. are always symmetric with respect to center of inversion I and cannot show IR active bands. Thus, in this module, what we have learned? We have seen how there is an interaction of internal electric field due to the vibration in molecule and external field responsible for IR radiation. The selection rules for IR spectroscopy have been explained by taking the example of water and POCl3 molecules. And these rules have been applied to both of these molecules, water and POCl3, and we have checked whether the modes of these molecules are IR active or Raman active. That is, we have checked their activity. Selection rules for Raman spectroscopies have also been explained. How to find Raman vibrational active modes for water molecules has been explained in detail. How to find Raman vibrational active modes for POCl3 molecules and water molecules have also been explained in detail.